All right. Here we go, guys. Here we go. Happy weekend. Happy Monday. I hope you guys are happy. Here's the same graph from notes 1. And yes, we've been messing with the same graph all this week. That's intentional. And we're about to do some very cool stuff. We're going to start off with some very simple stuff at first. We already know what this limit is. That's approaches 3 from the left, but we're going to do it with a table. How do we know? It's whatever this value is. And I think we said that value was negative 3 comma. Did we say it was 7, 6? Yeah, I couldn't remember. So here we go. I'm going to type this into my calculator into y1, 2x squared plus 5x minus 3. So let me get my calculator out. Y equals, clear that. Alpha, y equals, enter 2x squared. I already forgot. Was it plus 5x? 5x minus 3. And in the bottom, I have x squared minus 9, right? X squared minus 9. All right. In case you don't know what 7 over 6 is, 7 over 6 is 1.1666666. So this is a number that we should be approaching as we get closer to negative 3 from the left, which I think that's what we're doing. Yep, negative. So here we go. I'm going to type these numbers into my table. So second table, negative 3.75. It's just going to overwrite what I have there. Bam, 1.25. So I'm going to put that number in there, 1.2593. What's up, miss? And then the next one, negative 3.1. So negative 3.1, 1.1803. Then negative 3.01, negative 3.01, 1.1681. And then finally, negative 3.001, 1.1668. Is it approaching 7.6? Yeah, heck yeah, it is. 1.16666. No, let's not put that number. We're heavenly here. 7.6. Oh, okay. I need to talk about that. The power of pride. Sorry. That was a joke, but it wasn't funny. I apologize. Some people find religious jokes not funny. I think they're a little. Tell me why you do. I'm going to probably have to delete that from this YouTube video, huh? Okay, remind me. All right. Do the same thing from the right. Wait, was I approaching? Yeah. Do the same thing from the right, guys. If you're approaching negative 3 from the right, you're going to be approaching from 2.75, negative 2.9, negative 2.99, negative 2.99. And I should be approaching the same number, 1.66666 or 76. Oh, it's oscillating. No pattern. Does not exist. Yeah. But like at first I had no yeah, I just didn't even know like I got it wrong on purpose. I was like, okay, move on. But that was cool, right? The way the Delta had the calculator and you can put in numbers, get closer and closer. Yeah, that was cool. That was fun. So there it is, guys. Approach negative 3 from the right. And yes, again, it's approaching that 7.6 number, 1.16666. And you guys hook me up with the number so I can fill my table. What was the first one? 1.1304. What was the next one at negative 2.9? 1.1525. And negative 2.99? 1.1653. And a negative 2.999? 1.1665. Okay, perfect. So I'm approaching 7.6. No trickery there. That was that whole So limit as x approaches negative 3. It'll from the right and the left match. So there it is. And we probably could have skipped that page. Now it says let's complete the table as x approaches negative infinity. So negative 50, negative 100, negative 500, negative 1,000. So let's see if we get something here. Negative 50. I'm going to type in that number, 1.90. Then it has, what was the next one? Negative 100. Negative 100. 1.95. Then what did they go? 500 or negative 500? Negative 500. Oh, I'll show you right now. 1.99. And then what's the last one? Negative 1,000? 1.995. Put those numbers in. In case you're not getting decimals, you're probably getting fractions on yours, right? Okay, go to mode and then scroll down to where it says, you see where it says answers? And put DEC, that stands for decimal. Okay, so hook me up with those numbers, Abdul Kareem. What was it on negative 50? Huh? 1.9057. What was it at 100? 1.9515. And a negative 500? 1.992. And a negative 1,000? 1.9925. Okay. Yeah. What does it look like it's approaching? 2. Could we have done that by looking at the graph? Yeah. Could we have done that by looking at the expression? Yes. Link it to end behavior. If it has a horizontal asymptote, y equals 2. That's my horizontal asymptote. Link it to end behavior. The highest degree in the numerator, the highest degree in the denominator. So you just take the coefficient. 2 divided by 1 is 2. So anytime you see limit, if it approaches infinity or negative infinity, link it to end behavior. Are we in the clear? Okay, we should get the same number, well, not the same numbers, but the same trend. We should get the same trend for positive infinity. Not the same numbers because I think it's coming from the other direction, but it's going to be approaching the same value. So do the same thing, guys. Sorry. I'm going to take out the negative, and then we're going to go 50, 100, 500, 1,000. Yeah, if it approaches positive or negative, if x approaches positive or negative infinity, you should be thinking horizontal asymptote, if it has one. No, an infinite discontinuity is a vertical asymptote. End behavior. As x approaches positive, negative infinity, that's end behavior. So here we go. Hook me up with these numbers, guys. 2.64. What about a 100? What about a 500? Binary. And then 2. Perfect. What's the question?
My question is, why are we looking for like the vertical?
I'm not looking for vertical. Right now I've been looking for horizontal. Well, because these numbers are approaching very large values, I'm not approaching any vertical asymptote. That's end behavior. As x approaches positive or negative infinity.
Oh, okay.
No, you're good. Ask. We're good? Is everyone okay, or are we clueless? Okay. If we have a little clue, then we're okay. All right, notice this is approaching 3 from the left. So already, I just want you guys to observe, here's my vertical asymptote at 3. If I approach from the left, notice that I'm going to get large magnitudes in the negative direction. I don't like to say small because they're actually, but does that make sense? Okay, so we're going to get, if I fill this in, 2.75, 2.9, 2.99, 2.999, we're going to get large numbers, large magnitudes, but negative. So let's do that. 2.75, 2.75, and then negative 18. So then I'm going to do, what do they do next? 2.9, and then 2.99, and then 2.999. And check that out. Cool, right? All right, so let's see. This was negative 18. What was the other one? Negative 48. And then that was negative 498. And then what was this one? 4,998. Does it look like I have a pattern? Well, I mean, there is a pattern, but am I converging on any number? Yeah, I'm not. I'm not converging at any y value. So this behavior is negative infinity. You can also say it does not exist. It's the same. The y values keep getting larger in magnitude in the negative direction. Are we cool, guys? All right, let's do the same thing. Obviously, from the graph, let's look at the graph here. Obviously, from the graph, it looks like I'm going to be approaching a large magnitude. So it's not going to be a surprise that you're going to get a bigger and bigger number. 3.75. 3.75. 3.1. 3.01. And 3.001. There it is. Hook me up with those digits, guys. All right, what about 3.1? 50 what? 3.01? And 5,002. What am I approaching? Yeah. Infinity or does not exist. It's not converging. Both of those answers. Yeah. Infinity is the behavior. That's probably the one that they probably want better. How do we feel? Can we make a statement about horizontal and vertical asymptote when it comes to limits? All right, let's do the vertical asymptote first. If limit as x approaches some number from the left of a function, and you get what or what for vertical asymptotes? Perfect. Negative infinity or positive infinity, dot, dot, dot. We have a vertical asymptote at x equals c. It could also be x equals c from the one hand side. Okay, I'm going to slow down real quick just to make sure that we know. You do not have to have infinity and negative infinity for both directions. You can have it just for one and still be a vertical asymptote. Chavez, I've never seen that before. What do you mean? Let me show you. Don't write this down, just listen. That was supposed to be you guys. So if I did this, look at this. I can have, that looks like a vertical asymptote, right? And then I can do this. See? So it doesn't have to be from both sides. It could be a piecewise function. As long as from one of the directions, it's a positive infinity or negative infinity, and oh yeah, the next one's a demerit. I'm kidding, that's a joke. As long as it's positive infinity or negative infinity from one of the directions, that's a vertical asymptote. Are we in the clear? Okay, perfect. Now, if, let's do the horizontal one, limit as x approaches negative infinity or x approaches positive infinity of a function, and I get a value, that means, what does that mean? That means that y equals L is a horizontal asymptote. Does that make sense? Okay. I'm going to ask you a question. This is actually a real one. It actually came out on an assessment. I don't know if it was a university assessment or if it was a college board assessment, but it came out in an assessment. What is the most number of horizontal asymptotes a function can have? 2. Yeah, that's it. That's the most. Because you can positive infinity if you're approaching a number, negative infinity you're approaching a number. You can't. There is no such thing as the most. I have 5 horizontal asymptotes. No, the most you can have is 2. What's up? You can have 1. You can have none. But the most you can have is 2. You can have a horizontal asymptote like that, and then you have like another one down here where it goes like that, and that's it. And maybe in the middle there's something funky going on, or you can have one like this function here. This one only has one. This one just has that two. That one just has that. That one just has that two there. Because there's only two directions. You can only approach positive infinity or negative infinity. You know what I mean? And that's it. You can only approach those two. If I had, in case you're wondering, like, how does it look for two? Well, maybe, I don't know, maybe you have something like this. That one has two. Child, how do you know? As x approaches positive infinity, it looks like 1. If x approaches negative infinity, it looks like negative 1. Do you see it? Yeah. Positive, if I'm talking about positive infinity, 1 divided by 1, 10 divided by 10, 100 divided by 100, 1,000 divided by 1,000. If I'm talking about negative infinity, the numerator will always be positive. I'm looking at the blue. But the denominator will be negative. Do you see that, guys? So it'll be negative 1. Yeah. Negative 1 all the time. Do you guys see that? You okay, Tovar? You okay, Pollo? Oh, you guys are both Pollos. Sorry. Pollo 1, no Pollos, just Pollos. Okay. Here we go. We're just practicing now, guys. This is practicing, I think we're practicing horizontal asymptotes. Yeah, so these are the 3 rules. Don't be a robot. Make sure you remember why. Hey, no yawning. That's another demerit. And how many demerits am I going to pass out today? Here we go. The fine horizontal asymptote. Number 1, if the degree, the largest exponent of the denominator is bigger than the degree of the numerator, the horizontal asymptote is the x-axis, y equals 0. Why? Why, Chavez? Why? Pretend I have something like, let's just keep it simple, 1 over x. The degree in the bottom is 1, and I don't have a degree in the top. So as I keep getting larger and larger, 1 divided by 1 is 1, 1 divided by 10 is 0.1, 1 divided by 100 is 0.01, 1 divided by 1,000 is 0.001. Do you see what's happening? The bottom keeps getting larger, so my output keeps getting closer to 0. That's why y equals 0 is my horizontal asymptote. Yay or nay? If they were to tell you, Chav, what's the limit as x approaches infinity of 1 over x? So hopefully without thinking, you tell me it's 0. 1 divided by a huge number. Cool? All right, perfect. Ask. No, this one's 0. I'm approaching him. If I approach infinity, it's going to be 0. It's not going to be undefined. You're thinking about what if I approach 0, if x approaches 0. I can't divide by 0. If I'm approaching 0, then it's going to be either undefined. If I approach from the right hand, it's positive infinity. If I approach from the left hand side, negative infinity. Okay. Number 2, if the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. But I got to put an asterisk. Put an asterisk. Put an asterisk. Hallelujah, hallelujah. Put an asterisk. If the degree of the numerator is larger by 1 from the denominator, you have a slant asymptote. Luckily in calculus, we don't have to deal with it, but in pre-cal we did. We didn't go super heavy. I should have hit you guys harder, but just know that. So what did I say? Good. If the degree of the numerator is 1 bigger, you have a slant asymptote. If they ever ask you, if the professor ever asks you, find me the slant asymptote, what do? Synthetic division, long division. That linear expression is going to be your slant asymptote. It's always going to be a linear line if it's 1 bigger. Okay, so then you don't have if it's more than 1, if it's 2, you don't have, it has to be 1. Number 3. If the degree of the numerator and denominator are the same, the horizontal asymptote equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Pretty simple, right? That one's straightforward. Am I talking too fast? I'll slow down. Okay, I'll slow down. That's because I want to get through this real quick. All right, here we go. Let's see how much of this you know. The limit as x approaches negative infinity, try to do this as much as you can without a calculator, of e to the x. Do you remember how e to the x looks like? E to the x, I'm going to draw it right here for you guys. It looks like this. So as I approach negative infinity, what do you think this is going to approach? 0. Good job. Be confident. Be confident, boyo.
Oh,
Because I'm approaching to the left, right? Do you know how the graph e to the negative x looks? It looks almost the same, but like this, right? Good. So what is this limit? It's 0. Uh-oh, now I have an ln x here. Chop, I don't know how ln x looks like. It's growing really slowly, but it continues to grow. It's really the inverse of e to the x, but it's growing super slow. So this is, what is it? Infinity. Yes.
I just put an 8.
It grows really, really slow. Do we have any questions, guys? Hit me with your concerns. Hit me. Oh, because I don't have a horizontal asymptote. You don't reach anything. It just keeps getting larger and larger and larger. Very slowly, but it gets larger. Watch. So let me take out my little calculator here, and I'm just going to put y equals ln x. So here's ln, here's x. Now it grows very slowly. Look, I'm going to put 1. Well, 1 is 0. I'll put 10. I'll put 100. I'll put 1,000. Did I put more? I put more. It's not capped. It's growing very slowly. I'm not going to converge to any number. So even though this is getting larger and larger, well, so is the y value. It's getting larger and larger. You see it? Okay. All right. Check it out. Letter D. Let's see if we can do this. I have an ln of x on the inside, and it's ln of that. What do you think, Ramirez? Infinity. It's growing, but even slower. It's growing super mega slow. If you feel like you need to take a break, if you want to get up, go for it. Shout. All right. Here we go. Ready? Now let's see. I have x approaches infinity, 10e. Look what I have on the inside. E to the negative x in there. Chav, I don't know. I can't do these. Yes, you can. All of them, all e to the negative. It doesn't matter how small of a number or quotient it is in the front. All of them, e to the negative x is going to look like this. So, no, this is, x is approaching infinity. So this graph that I'm looking at the inside specifically, what I'm circling in blue, only what I'm circling in blue. So if that in blue is approaching 0, what is this limit? 1 over 2. Yeah, because the 10e to the negative to the 0.001x, that's approaching 0. So what's 1 over 2 plus 0? 1 over 2. Do we see what we did there? Shout. No, shout. Okay. All right. Limit as x approaches infinity. I have to look at end behavior, right? What's my highest degree in the numerator? It is. Give me the coefficient in front of that. How do you do it so quick? Look, guys, just take 7 times x times x. You don't have to worry about floating. In the bottom, it's x squared. Are the degrees the same in the numerator and denominator? So what is my end behavior? 7. Let's go to letter G. What is this limit? 0. Why? That's right. That's my end behavior. If they were to ask you in Algebra 2, what's my horizontal asymptote? You would say y equals 0. Letter H. Does not exist, or you can say infinity. Because the degree of the numerator is larger than the degree of the denominator, so you don't have a horizontal asymptote. It just keeps growing, unbounded. Does that make sense? All right. Letter I. Yeah, 7 halves. Sorry, I didn't see that. 7 halves. Cool or not cool? All right, we're going to get you in a little bit. Letter J. 5. Did someone say 5? I thought I heard someone say 5.
Because if
Yeah, end behavior, you're just looking at the x squared. Square root of x squared is x. Letter K. It's not 5. Why is it negative? I just heard you, Abdul Kareem. You said negative?
I didn't say that.
Okay, yeah, but give me a better answer. Well, okay, let's stop. You guys are close, but we're not. The reason why it's negative infinity. Let's see if this makes sense. The denominator will never be negative because you're squaring it first. So notice, yes, I'm approaching a negative infinity. So let's pick a random number, like a big number. Negative 1,000 squared. I'm squaring that number, whatever that number is. Now it turns to a positive, and then I take the square root. I'm back to 1,000. Does that make sense? But then in the top, it's 5 times negative 1,000, and that's what stays negative. The numerator stays negative while the denominator stays positive. Do you guys see that? So that's why it's negative 5 in the top. The numerator will always be negative. Does that make sense? I forgot what I wanted to put here. Oh, okay. I think I remember. All right. I don't remember. I think I remember what I wanted to put here because I put let's chat. I think that I wanted to say that if you have some number divided by 0, I don't want to say 100% of the time because it's not always. 99% of the time, you will have a vertical asymptote. If you insert the Chavez, what are you talking about? Number divided by 0. If you insert, like, let's say, look at this one right here. In a little bit, we're going to be doing that one. If you do limit, look, let's just do one real quick. Limit as x approaches 2 of 1 over x minus 2. That one for sure, 100% does not exist. I'm not going to put up behavior, but it has different behavior from the right and from the left. Does that make sense? Can you tell me without doing much calculations in your head, can you tell me what this behavior is? Is it positive infinity or is it negative infinity? Without trying to imagine it in your head. 2 from the right side. Yeah. And then this one here, I thought you knew. And that one is negative infinity. Yeah, let me explain why, guys. The numerator is always 1, right? But let's see, if I approach 2 from the right, so think about it. It's like what we did when we did our tables. If I approach 2 from the right, I'm approaching with numbers slightly bigger than 2. 2.1, 2.01, 2.001, and 1 divided by a super small number, positive infinity. If I approach from the left, I'm talking about numbers slightly smaller than 2. 1.9, 1.99, 1.999. 1 divided by a super small negative number, negative infinity. Does that make sense? What's up?
Okay, but like sometimes like we'll have graphs where like it's split. So when you're approaching it from the right, you get a negative.
Yeah. And then to the left, positive infinity. It depends on what graph you have. All right, so let's look at this equation right here, guys. So example 2, or question 2. Find all vertical asymptotes for this graph. Justify your work by showing limits. Show work for full credit. Okay, before we can even start, can we factor this out? We can factor. What 2 numbers give you 6 that add up to 5? No. 3 and 2. X plus 3, x plus 2. And in the bottom, I can factor out an x. And I have x squared minus 4. But notice the x squared minus 4 is the difference of squares. Do you guys notice that? All right, so then here's what I have. X plus 3, x plus 2 over x parenthesis x plus 2, x minus 2. And I'll zoom in. Yeah, maybe showing it with limits was dumb. I think it's just better if you just do it algebraically. Which 2 are my vertical asymptotes? Which ones cancel? What factors cancel in this? X plus 2's cancel. So now what are my vertical asymptotes? No, negative 3 is a 0.
So it'd be 0 and 2.
0 and
So
2.
you have to do whatever.
Because you cannot divide by 0, right, guys?
Yeah.
All right. So x equals 0 and x equals 2. And I know some of you guys are tired. I don't think you guys got good sleep. So try to get some sleep tonight, guys, to catch up. So 0 and 2. Now, I can tell because some of you guys are blinking really slow. What's up? From this one right here. There's nothing else that it can cancel out. You know what I mean?
Oh. So you're saying that
You can't have a 0 in the denominator. Okay, say it again.
you're saying that the vertical asymptotes come to the denominator.
Yeah,
Is it equal to 0 to the denominator?
correct.
We have 0.
Yeah, that's where I have a vertical asymptote. I don't have a 0, negative 2 because those canceled out. From x minus 2. 2 minus 2 is 0, right? Yes. That's a vertical asymptote, x equals 0. Right?
You said you can't have 0. Is that something else?
Every time you have a 0 in the denominator, it's either going to be a whole or a vertical asymptote. So at x equals 0, I see you, miss. At x equals 0, that's a vertical asymptote. What gives you zeros in the denominator? Whatever gives you zeros in the denominator is either going to be a vertical asymptote or a whole. All right, what's up? Why do we what? Oh, well, I have x by itself, and you can't divide by 0. So if I plug in a 0 in there, it will be undefined. If it looks like this, yes. You've always done it. If you had a function, like if you have something like this, and I told you where are my vertical asymptotes, well, that one was simple. You just did this, right? And you said, I have a vertical asymptote at negative 2, and I have a vertical asymptote at 2. But if I have something like y equals 1 over x squared plus 3x, and I say, where's my vertical asymptote? Well, you just cancel out, factor out an x, and you get x plus 3. And then that one has a vertical asymptote at 0 and at negative 3. 1 is nothing. You have nothing in it. Like, your vertical asymptotes depend on the denominator. I don't have x equals 1 will not give me a 0 in the denominator. The only way you can get vertical asymptotes happen when the denominator is 0. Also, wholes happen that way. Do you know what I mean, Alvarez? No? Okay. This is my denominator, and this is my numerator. The numerator will only give you your x-intercepts, where this function, where the y's are 0.
So there were an x on the top. That would be your.
Well, if there were an x on the top, that x and that x would cancel out, and I would have a whole at x equals 0.
What if there were like only an x on the top?
Okay. If I have something like this one right here, but with an x on the top like that. Okay, then I have a 0 at x equals 0. I have a whole. No, it's not a whole. I have a 0. X-intercept, in this case, it would be going through the origin, which would also be a y-intercept. You know what I mean? Ask. All right, so here's the question, guys. I'm gonna help. So, let's see if we can sketch this without the assistance of a calculator, and then we'll use a calculator to help us out. So if I have something like this, y equals, and I'm gonna say x over x squared minus 4, right? So this is, you know what? Let's make it even better. Let's make x minus 1. Yeah, you can. Well, for now, just listen, because I want you guys to really absorb this. So I have this, right? So I'm going to have x minus 1 on the top, and on the bottom, I'm going to have x minus 2, x plus 2. Are we still okay? Okay, so what do I know from this? I know that I have a horizontal asymptote of y equals 0. I know that I have a vertical asymptote of x equals plus minus 2. I got 2 of them. Positive 2 and negative 2, right? And then you're like, well, what about this x minus 1 in the top? That's just going to tell me where I have an x-intercept. I have an x-intercept at 1, comma 0. Yes, you did. Spanish book. Does that make sense? So if I were to graph this, I don't know if it's being graphed super awesome, guys. Here it is. I'm going to say that's 2. I'm going to say that's negative 2. I see that I have an x-intercept at 1, 0. So I go to 1, 0. I'll put a point. See? And then let's see. It's probably going to look something like, probably have to go at 0. Okay. At 0, comma, negative 1, positive. So negative 1/4. So I know I'm going like this. So it's probably going to look like this. See? How did I do that? Chavez, how did you do that? I just plugged in numbers. I plugged in a 0, I got a negative on the top, and I got a, actually, hold on. Negative divided by a negative is a positive. It's a positive 1/4. Darn it. It's up here. It's the other way around. Yeah, it's because I'm going real fast. Sorry. It looks like this. See? If I plug in a 0, I get negative 1 over negative 4. Right? Which is a positive 1/4. Okay, now how do I look over here? Well, let's approach 2 from the right. I already know it's a vertical asymptote. In the top, no matter what, 2 minus 1 is a positive, right? Because I'm choosing really close numbers. Now, in the bottom, a number slightly bigger than 2 minus 2 is going to be positive. And then 2 plus 2 is going to be positive. So positive divided by positive is a positive, so I know that it looks like that. So it looks probably like this. Now I'm going to go to negative 2. And I'm going to approach it from the left. So negative 2, like negative 2.1. Negative 2.1 minus 1 is a negative, so remember that negative. And then negative 2.1 minus 2 is more negative. And then negative 2.1 plus 2 is still negative. Negative times a negative is a positive. I guess I didn't have to do that. I could have gotten this one. Negative divided by positive is a negative, so it's going to look like this. It's going to look like that. Let's see if it's true. Should we? I don't think I'm fake. I hope I'm not. Let's see. Yeah, I'm going to graph it. And let's see if I'm fake or not. I'm not fake, guys. I'm math life for life. X minus 1, x squared. Some of you want me to fail, right? Some of you are like, and I hope he's wrong. Look, it's correct. I did it. Let me zoom out. But Abdul Kareem, I bet you, is looking at me like, I hope he gets it wrong. She's a hater. I'm kidding, Abdul Kareem. Do you see how we did it, guys? This is going to be your lab tomorrow. We're going to be doing sketches. I hope, don't worry, we'll get through it together. Okay, let's continue. No, don't be scared. Let's look at this question. Question 3. Limit as x approaches negative infinity. Remember what we told you about squares and square roots. So if I approach negative infinity in the numerator, will the numerator always be positive? Yes. So your end behavior for the numerator is square root of 8x squared. In the denominator, it's just x. The denominator, because I'm approaching negative infinity, the denominator is going to be negative. So I already know that my output better be negative. So it's between A and B. Yes. Yes. X is approaching negative infinity. I'm looking at end behavior. I notice that in my numerator, I have to square it first, and then square root it. So it's going to have to be positive. Must be positive. In the negative, I don't have a square root. It's just x. Because I'm approaching negative infinity, it's going to be negative. That makes sense? Okay. Here we go. I know I said it real fast. I'm going to slow down. You gotta tell me, guys. You gotta tell me that I'm going fast. The square root of 8 is 2 square root of 2. That's my coefficient. And then the square root of x squared is x. So I'm gonna put the x right there next to the 2. In the bottom, because I'm approaching negative infinity, write negative x. Does everyone know why I wrote a negative in the bottom? Because I'm approaching negative infinity. Perfect. What's gonna cancel? The x's. 2 square root of 2 divided by negative 1. Do you see how we did it? Perfect. Yes.
Why did you just get rid of -4?
End behavior. It's like spit. If you spit in the ocean is the square root of 8x squared and the 4x is spit. It's not significant. Does that make sense? If you spit in the ocean, does the ocean rise? It doesn't make sense at all to you guys?
Oh, okay. If you say it like that, it makes sense.
Yeah.
They spit in ocean.
If you spit in the ocean, does the ocean rise? No. So your ocean is 8x squared end behavior. And the 4x is spit,
So is it just like the first term?
the highest degree. Because what if I have a first term that's x and I put the higher degree later on? Which I have done in the past. What's up?
Sorry, I didn't get what you were saying. Like, why you said it seems like a lot of people why is it not?
Because I'm squaring it first. Anytime you square something, it turns positive. A negative times a negative is a positive. You always square it. The end behavior, you're going to square it first. So if you choose any value, any x value, as long as it's the same value, you're going to get a negative. Like, look, let's choose x equals 10. So you're going to go square root of 8 times 10 squared over negative 10. Well, that means, look, the square root of 10 squared, that's going to be 10, square root of 8 over 10. Oh, that's going to be a negative down here. Negative square root of 8, there it is. You know what I mean? Okay. How do we feel? Okay. All right, this one's kind of hard, guys. A little bit, but it's not, well, yes and no. Do you know what ln of 1 is? Yeah, what's ln of 1? Yeah. It is 0.
Because of the way the graph works?
Ln of 1, ln of x is, at the very minimum, guys, we should know this. The ln graph crosses the x-axis at 1. Yes or no? Okay. Because you took algebra. All right. Here we go. If I approach 1 from the left-hand side, if you're to the left of ln x, of ln1, of ln x, you have very, very, very small negative numbers. Do you see that? If you're to the left of 1, right here, if you're to the left of 1, you're like, I don't know, somewhere like right here. And those are very, very small negative numbers, right? So when you take a number like 1, because x is practically 1, and you divide by a very, very small negative number, 1 divided by a very small negative number is negative infinity. And those are hard because you have to have some previous knowledge. One, you got to know that ln of x intersects the x-axis at 1, 0. And then 2, you got to know that to the left of 1, the y values are very small negative y values. Are we cool? Don't worry, I'll try not to give you those. Number 5. Okay, this is the last one, and then the rest are just practice problems. All right, number 5. Before you do anything, immediately you say, I have a 0 on the bottom. I know that I have a vertical asymptote because I have a number divided by 0. Do you guys see that? 2 times 2 is 4, 4 minus 4. Okay, perfect. The top will always be positive. 5 times 2, 10, plus 1, 11. I know that I'm approaching from the left, but it's going to be a positive number because you're pretty far away from 0 anyways. Are we okay? So all I care about now is I already know it's going to be positive infinity or negative infinity. Is my denominator going to be positive or negative? That's all you care about now. So let's see. From the left, 2 times 1.9. Is 2 times 1.9 going to be pretty close to 4? Yeah, but is it quite 4? It's like 3.9 something, right? 3.8, 3.9. If 3.8, 3.9 minus 4, is that positive or negative? So it's going to be a negative. Yes. The numerator is going to be a positive no matter what, right? You're approaching from the left. So 2 times 1.9, 2 times 1.99, 2 times 1.9999999. It's not quite 4. It's like 3.9, 3.99, 3. And then 3.99 minus 4 is a negative number. Do you see that? Yeah, that's why these are hard, guys. All right, we're done. Well, kind of. No, I haven't been. I keep forgetting to buy some for you guys, like crackers and stuff. Keep reminding me. Okay. Here we go, guys. This is just practice now. See if we can do this. You guys ready? All right. 1 minus secant squared of 6x over 2x squared. Positive or negative? This is equivalent to limit as x approaches 0 of negative tan squared of 6x over 2x and all that quantity squared. I'm about to expand it. You guys ready? Limit x approaches 0, negative tan of 6x over, I guess, one of the 2x's, and we'll move the 2x in a little bit. Giant parenthesis, tan of 6x over one of the 2x's times, and a little bit I'm going to move stuff to that one. I haven't changed anything, have I? Okay, I'm going to get rid of these 2's, and I'm going to put them over here. Are we okay? Here, if you have a colored pencil or a colored marker, here's where it works really well. What do I need in bottom of this tan 6x? A 6. All you know, side note, guys, all you know is this. Limit as x approaches infinity, 0, of tan of happy face over happy face is equal to 1. If I put a 6 in the bottom, I got to put a 6 in the top. What does the second middle term here need? Another 1 and another 6 there. So here we go. I have negative 1 times 1 times, I guess we can reduce those, but I guess we'll leave them. 6 times 6 is 36. 2 times 2 is 4. 4 goes into 36 how many times? 9. There's my answer. How do we feel? Yeah, negative 9. Okay. Here we go, guys. Next one. You look at it. Can I do direct substitution? No. Here's what we're going to do. Remember from pre-cal that 1 over cosecant x is equivalent to sine x. So you don't even need a lot of pre-cal. You just need baby pre-cal. Limit as x approaches 0. I'm going to move that cosecant with the 3x up. 3 sine x over 4x over 4x. I'm in business. No, 3 sine x over 4x. Oh, yeah, you're right. The 3x is the argument. Man, what am I doing? There we go. Now we're right. What's up, Alvarez? Oh, because of the side note, I guess I should have written it like this. 1 over cosecant 3x is equal to sine 3x. Okay. So here we go. Side note, limit as x approaches 0, and since I have it in the top, I'm going to write it like this. Sine happy face x over happy face x is equal to 1. So I'm going to expand this. Limit as x approaches 0, giant parenthesis. I'm going to put 3/4 times sine 3x over x. Have I changed anything? Get your colored pencil, and I'll wait. I'll slow down. What does the bottom need? A 3. I'm going to put another 3 here in the top. What's my answer? Yep, it looks like it's 9/4. How are we feeling? Number 8. Don't worry, guys. We'll stop in a little bit. We'll stop. I know we're getting tired. We're reaching our edge. Can I do direct substitution? No. So we're going to have to do something. Right now, with what we have, we don't have a property for the one that like this one looks. So that means we're probably going to have to multiply by the conjugate or something like that. We've done that before, right? Like in pre-calc and stuff. So you see that 1 minus cosine on the bottom? I'm going to multiply by 1 plus cosine. I'm not changing anything because look, that's still a 1. I'm not going to bother foiling. So here we go. Limit as x approaches 0, giant parenthesis. And let me see, how am I going to write it? 5x squared 1 plus cosine 2x over, and the bottom I'm going to write it like this. 1 minus cosine squared of 2x. Is anyone confused with what I did? 1 minus cosine, 1 plus cosine is the difference of squares, guys. So if you fold it, you're just going to get 1 minus cosine squared. Hopefully you remember, 1 minus cosine squared is equivalent to? Perfect. Limit as x approaches 0, 5x squared, 1 plus cosine 2x, close, over sine squared, and I got to keep the argument, 2x. You still can't do direct substitution, but you can use your property. So here we go. I'm going to expand it. Limit as x approaches 0, giant parenthesis, and let me see. I'm going to write it like this. I'm going to put the 1, excuse me, plus cosine 2x, and then I'm going to say that's over 1 times, and then I have a 1, 5. I'm going to put the 5 right here. Can I do that? Okay, so there's my 5 times that. And then I have one of the x's over sine 2x, and then another one of the x's over sine 2x. Have I changed anything? Take your colored pencil or colored marker. What do I need in the middle term in the top? X over sine 2x. I need a what? I need a 2. If I put a 2 in the top, I better put a 2 in the bottom. And the other one as well, I need a what? 2. And I put another 2 in the bottom. Do you guys see what I did? All right, so let's see what we have. We have, this is obviously a 1, and this is a 1. So 1 times 1 times, let's see, cosine of 0 is 1. So I have 5 times 1 plus 1 is 2 over 2. The 2's cancel out, so my final answer is 5. Oh, nope. There's a 4 on the bottom, not a 2. So my final answer is 5 over 2. Right? Yeah. Cosine of 0 is 1. So 1 plus 1. X is approaching 0. So I have a 0 inside. No. I plugged in the 0 in that. And then cosine of 0 is 1, right? What's up? You okay? Okay. Boyos. You guys okay? Ask. Where? Dime. ¿En el principio? Ah, okay. Okay. Ask, please. All right, last one, number 9. Can we do direct substitution? Say yes. Yes. Look, the denominator is an x, and this x is approaching 9 pi over 4. Direct substitution galore, guys. Cosine 9 pi over 4. Oh, Chav, I don't know if I can do that. Yes, you can. Over 6 times 9 pi over 4. What is cosine of 9 pi over 4? You don't need. Come on in. Square root of 2 over 2. Guys, if it were 8 pi over 4, that's 2 pi. You're only pi over 4 more, right? Excuse me. Cosine of pi over 4 is square root of 2 over 2. So you have square root of 2 over 2 minus 1 over, what's 6 times 9? 54? Oh, 6 times 9. So 54 pi over 4. We're going to do a keep change flip in a little bit. You can actually leave it like that, but let's do better. See that 1? I'm turning it into 2 over 2. So square root of 2 minus 2 over 2 times 4 over 54 pi. So let's see what my final answer is. I'm going to have 4 square root of 2 minus 8 over 54 times 2. Oh yeah, I could have just done this. 2 goes into 4 twice.
What are you doing?
Oh, I'm just simplifying it. Can I not do that? I think it's correct. Yeah, it's correct.
Yeah.
Okay, where did I lose you guys?
We started at
Let me explain. So cosine of 9 power 4 is square root of 2 over 2, right? And then that 1 I can turn into whatever I want. So that 1 is 2 over 2. And then I do keep change flip. Right? So square root of 2 minus 2 is the numerator. 2 is the denominator for that one. I have a 2 down here, but it goes away. I'll show you why. Times, and then I flip this. Yeah, it was 4 over 54 pi, but I reduced it. It was 4 over 54 pi. But remember the 2 that I had down here? 2 goes into 4 twice.
Oh my god, Slay. Sorry, Tom. You're not even
Remember the 2 that I had down here? 2 goes into 4 twice. So I turned out to 2. All right. This was the original. I'll put it in green. I had a 2 down here, and I had a 4 right there. But how many times does the number 2 go into 4? What? Twice, right? It goes in twice. Keep change flip. It was originally a 4, miss. It was originally a 4. But then I said, how many times does the number 2 go into 4 and it turned into a 2? Do you know what I mean? Paola, I want to make sure that you got it. Okay.
Because all you're saying is you're like simplifying it, right?
Yeah, all I'm doing is simplifying.
I can still just do the.
Yes. You can do 4 square root of 2 minus 8 over 50, 50, 108. You can do that and then reduce everything by 2. Don't worry, Silvana, I'll help you right now. 2 square root of 2 minus 4 over 54 pi. We got the same answer. Yes. I just hadn't distributed the 2 that I had over here. Yeah. You guys, oh, well, let me answer Silvana. What's up, Silvana? No. What's it? You got it? For sure. Okay, what's the question?
Why is there 2 kind of just like square root of 2 minus 4 in the last year? Oh, sorry. Did we simplify it?
I already did. That's, maybe it can be simplified more. Where am I? Okay, so it's going to be square root of 2 minus 2 over 27 pi. That sounds legit. Should we check? You know how you can check this answer, guys? Okay, I'll tell you. I didn't want to tell you guys, but you guys will be honest. There's something called Wolfram alpha. And I should have Wolfram. Do I have it? Nope. Okay. Wolfram, right here. So check it out. I'll put the word limit. Let's put that last one that we got. LIM. And then I put my expression. Oh, did you have a question, Romero? Oh, sorry. What did I have in the numerator? Cosine or sine? Cosine. Cosine of just x,
minus 1.
but that's not the argument, right? Okay, and let me close this. Divided by 6x. I'm going to put that in parentheses. Sorry that we're taking long here. And check it out. I'm going to put comma. And then I'll put x, comma. And then I put it where I'm evaluating at. What was it? 9 pi over 4? 9. And I'm going to have to type in pi, I think. Pi over... Sorry it's taking forever on this thing. And then close. And I'll check it out. Look, we got it right. They do it differently. Oh, look, here it is. Square root of 2 minus 2 over 27 pi. Cool, right?
Where's the 27?
Right there.
Oh, it's just 54 divided by 2.
Right there. How come it changed it? It changed it. Hold on, let me... Well, it doesn't matter. Square root of 2 minus 2 over 27 pi. Oh, that reduces what we have to that. If you put a 2 in, if you reduce everything by 2. They put the negative in the front. I don't like that. Because it looks like the whole expression, that negative tends to float sometimes. What's this website called? Wolfram Alpha. It's super powerful. You just saw what we just did. This is how you type in your limits. Limit, and then you type in your whatever it was, comma x, comma what is it approaching, and then it'll give you your answer. See, square root of 2 minus 2 over 27 pi. Cool or not cool? Okay, I feel like we're pretty close to like not be functional. I feel like we hit you guys pretty hard. I do have some more, but these can wait for tomorrow. If you guys want to wait for these for tomorrow, it's just over exponential functions, limits. So you want to wait for those until tomorrow? All right. So see if you can take care. I do have well, I'll pass it out for you guys.
My physical activity work that was the Friday that was.
Yeah.
Did you hate it?
No,
Oh. But you have it.
I have it. All right, guys. Take out your notes from yesterday. This is going to help a lot with the activity. This is going to help a lot with your activity that we did yesterday, where in the beginning I put behaviors of functions, and then I take them away. What's that?
Is anyone in need of service hours? Cutting these things out whenever you have availability would be lovely. Oh, did they come out?
Yeah, that's fine. Yeah, put them over there and she'll grab them. She'll grab them soon.
Where do you want them? Where do you want them? I'll just leave them in my room.
Okay,
If I get bored, maybe start, but like.
no problem. All right, guys. Later, miss. Ready, guys? Okay, focus, guys. So, does everyone know how y equals e to the x behaves? Okay, so probably this is the better graphs that we should know. Y equals 2 to the power x and y equals half to the power x. If you know those graphs, then you know all the exponential graphs. So let me show you how y equals 2 to the power x looks like. Y equals 2 to the power x looks a lot like e to the power x. If I tell you, and I'll put them in color code so we don't mess them up, 2 to the negative x. By the way, you can also derive these. So in case you're wondering, Travis, how do you derive them? 2 to the power x. 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. So you can see, as x gets larger, so does the y. What about 2 to the power negative x? Well, let's see. 2 to the power 0 is still 1. 2 to the power negative 1, I'm saying x equals 1. If x equals 1, 2 to the power negative 1, that's a half. If x equals 2, 2 to the power negative 2, that's a fourth. If x equals 3, 2 to the power negative 3, that's an eighth. Do you guys see what's going on? So this graph looks like this. Does that make sense? But notice, look at the behavior that happens. I'm going to switch the colors. So if you have colored pencils, or look what happens if I do this. 1/2 to the power x. 1/2 to the power 0 is still 1. 1/2 to the power 1 is a half. 1/2 to the power 2 is a fourth. 1/2 to the power 3 is an eighth. What do you notice? It's the same as the 2 to the negative x. Do you guys see that? That's how powers behave when it's a number between 0 and 1 like that. Now look what happens if I do y equals 1/2 to the negative x.
Oh my god, is it gonna be like
1/2 to the, yeah, it's going to look like 2 to the x. 1/2 to the, if x equals 0, it's still going to be 1. But if x equals 1, 1/2 to the negative 1 is 2. If x equals 2, 1/2 to the negative 2 is 4. If x equals 3, 1/2 to the negative 3, because you're using the law of exponents, right? Negative 3 means it goes up, so 2 to the third is 8. So this one's going to look like this. OMG. Do you guys see that? All right, and now it's just little basic transformations. Look at here in the bottom. Well, we already know the 2 to the negative x. That one looks like that blue one there. I'm not going to color code this, guys. I'm just going to go back to my red color. So 2 to the negative x. This one has a -4. So that one looks like 2 to the x, but then that -4 moves 4 down. Vertical shift 4 down. So that one looks like and it goes through -3. Is everyone okay with that graph? Okay. And then if I put a negative in front, so pretend that's like 2 to the power x. If I put a negative in front, all that does is reflect it across the x-axis. So instead of looking like this one, I look like that. Maybe I should have exaggerated quadrant 4 instead of quadrant 1 and 2 there. How do we feel? What's up? Why is it what? Oh, because all of these are at 1, 0, 1. So remember, all these limits as x approaches negative infinity, that's a 0, that's a 0, that's a 0. But then I brought it down 4 times. So since I brought it down 4 times, that -1, if you bring it down 4 times, it's a -3. What's up?
Because, well, I mean, if you're just gonna say like the y-intercept is like when it intersects the y-axis, x equals 0, e to the power of 0 is 1, so 1 minus 4.
Yeah, you can also say e to the 0. Yeah, you can say that. You must have taken algebra too. I'll stop. Does that make sense, guys? Yes, ask. Only for if I approach negative infinity. Yes. Cool. So here's what I'm doing with these, and then you'll notice in your activity in the beginning, or towards the end, in the beginning you notice that I have graphs because I'm trying to help you out. Let's see if we can do this without graphs. These are the same ones, really. Ready? So notice that I have a 2/3. 2/3 is between 0 and 1. So this behaves a lot like 1/2. Are we okay? And it's to the power negative x. Who cares about that -1? All that means is horizontal shift. So to the power negative x. So I'm going to look at the half to the power negative x. So this is how it looks like. Like this one here in black. Does that make sense? Yeah, so it looks, that 2/3 looks a lot like the half to the negative x. Like this one. And I'm approaching, do I have a limit there or no? Limit that's approaching infinity. Well, if I approach infinity, doesn't this look like it's unbounded? So it's infinity. How do we feel? All right, same thing, but this time I have a negative in the front. All that does is reflect it across the x-axis, and I'm still approaching infinity. So it looks like it's still going to be, yeah, but negative. Does that make sense, guys? Gonzalez, you okay? No, ask. It's all good. I make mistakes all the time. The 2/3 to the negative x should look like this one. And then with a negative in the front, it just means it reflects across the x-axis. So it probably looks like that. And I'm still approaching infinity. I know I see a horizontal shift up 3, but I'm still approaching infinity, so it's still going to go down forever. All right. 0.4. Is that a number between 0 and 1? And it's to the power x, so it's going to look like that one in green. And I'm approaching negative infinity. Oh, man, they're all going to be infinite. So it looks like I'm going to approach negative infinity, it looks like. That was not on purpose. I wanted it to approach something. Did I mess up? Yeah. 0.4 to the power x looks like that green one. But I have a negative, so all it means is, all that is doing is this, reflecting across the x-axis. And I'm approaching negative infinity, so...
So if it was approaching like this, infinity or
No, negative 4. Yeah, so that's a good question. Yeah. Limit as x approaches infinity. I'm going to update this. I'm going to add it. Limit as x approaches infinity for negative 0.4 to the power x minus 4. This one would have been negative 4 because of the horizontal shift down 4. Because it looks like the one in green, right? But the one in green would have been down like 4 units. That makes sense, guys? Okay. Well, okay, yeah. Reflected, but yeah. Oh, look, here it is. Darn it. That one's negative 4. That's the one that I just wrote right here. Yes. That point, okay, so I'm gonna go ahead and go slow. If I had 0.4 to the x like that. So if you want to know how to do it by yourself, just pretend like that's like 0.5. 0.5 to the power 0 is 1. 0.5, 1/2. To the power 1 is a half. Half to the power 2 is a fourth. Half to the power 3 is an eighth. So that graph looks like this. But then I have that minus 4 there. Well, okay, let's first go slow. But then you see that negative there in the front? It reflects it. So it looks like this. And I'm going to erase it again a little bit. And then you see this minus 4 right there? That brings it down how many times? 4. So I'm going to be right. That's a negative 4. And it's going to look like this. Why is it not what? It's not approaching 0. If the limit was 0, I have a y-intercept. Well, it's not a negative 3. It has a y-intercept of negative 5. Because this value right here is negative 5. You know what I mean? Because they're reflected. No? Okay, I think what you're thinking of this, Alvarez. Like you see this one right here? This one's not reflected. So this one has a y-intercept of negative 3. But I'm not looking for the limit as x approaches 0. I'm looking as x approaches infinity. So as x approaches infinity, I'm looking for that horizontal asymptote, which is negative 4. Do you know what I mean? All right, guys. Did that help this little bit? Did today help? I know it was hard, but did we do like a lot of productive struggle where we learned a lot?